I'm going to look at all of them again. And I get a whole lot of them, and I have to start over and look which ones are locally solvable, which ones have points, which ones don't have points. And hopefully, I will reach a point where everything that is locally solvable has points. So that is the problem of the algorithm, that we do not know whether SHA is finite. That would be what is happening here, the 4 torsion of SHA. If my SHA group has no elements of order 4, then all of those that are locally solvable here would have points. Okay? But if there is a 4 torsion point, I might find it here. And I have to go one layer up. So I would be able to go to some layer where that doesn't happen, but we do not know that SHA is finite. So for all we know, there could be some SHA that has 2 torsion, 4 torsion, 8 torsion, 16 torsion, and so on and so forth forever, and my algorithm in quotes would never end. We do not know that. The conjecture is that SHA is always finite, and it is proved in some cases that it's finite, but we do not know in general that all the elliptic curves have finite SHA. Okay.
Álvaro.
Yes.
So are these C deltas elliptic curves?
So those are called, these are twists of elliptic curve. So these are some other, this first layer, these are some other like genus 1 curves.
Okay. Well, we put them in
These are
form, and then use the E1s to make the further.
No, because these are genus 1 curves that I don't know if they have any points. So I don't have an origin to begin to do the everything we know. So these are just some genus 1 curves that are some like abstract twists of the elliptic curve itself, and then you're trying to find points in those, but whether there are points or not. So you're trying to decide if they are elliptic curves themselves or not.
Maybe you answer this later, but how do you get the equations for the further twists then?
Well, that is the problem. That, I mean, these ones I showed you how to do it. These ones are already quite tricky, and I think Magma can do 4 descents. Can it do 8 descents at this point? So Magma has implemented 2 descents, 4 descents, and then 8 descents, and nothing else. There's no farther descent. The equations just get too complicated to write down. And I think there are several descents that we know include 5 descents, 3 descents, but it just gets very complicated how to find those equations. If you take a real course on elliptic curves, this whole picture comes after the fact. You define the Selmer group from cohomology, and the Selmer classes are cohomology classes. And out of the cohomology, you can come up with algebraic equations for those, and those correspond to those are written here. So to find out from the cohomology explanation of the 17 descent, what are the equations that give you those homogeneous spaces, it's very hard to do, and then in the implementation would take forever if we actually know how to do it. Okay. Yeah.
So when we go to this irrational,
so this is the easiest descent that I've presented because you have the full 2 torsion. There is another descent that is easy to implement. That is the 2 isogeny descent, which is the case when you have just 1 point being rational. That's also easy to implement. When you have no points of 2 torsion defined over Q, what you have to do is like, well, I want my points to be defined over the base field, so I increase my base field. So you go up, essentially you go up to a field where you have a point, and then work there and do everything again, but at that level in the number field, and then try to bring them to see what there was actually defined over Q in the first place. There are workarounds. You don't have to actually go to a number field, but basically that's the idea. So for an elliptic curve that has no no 2 torsion defined over Q, the algorithm is a lot more difficult to explain.
No, we do the 4 descent.
No.
No, just no.
There's a way to create these without, you don't need to have for those to be just to do it over Q, you don't need the fourth torsion to be defined over Q. But there's a machinery that you have to do to be able to do that all over Q that basically involves going up to another field and working there and coming back. Okay, so I have like 10 minutes left to talk about the Birch-Schroeder conjecture, which is the following. So we've done some algebraic methods and maybe succeeded to some extent that we can actually, at least for small coefficients, we can get around and find the rank. So are there analytic ways to find the rank? Is there an analytic approach to find or estimate the rank? Well, that is exactly what Brian Birch and Sinnerton Dyer were trying to do in the 60s. So Birch and Sinnerton Dyer had the following idea, which is that if I have an elliptic curve, and if this elliptic curve has high rank, I can try to see those. I don't know how to find them, but if I reduce modulo p, I go to a finite field, and then there's only finitely many numbers to play with. But if there are points of infinite order, many of those should reduce, and I should see many points of finite order also. With finite order, I can just do a finite computation and find all the points and see how many there are over there. So there is this thing that's called the reduction of an elliptic curve. And then I'm working with my elliptic curve, but with points modulo p. So now this is going to be E tilde, and E is now defined over Fp. Now the problem is that I can go down and start with an elliptic curve, and all of a sudden here I get something that is singular. Okay? So I have to be worried about that first. So from E to E tilde, I can get good reduction. Those, by the way, are the primes that do not divide the discriminant of my elliptic curve. I can get bad reduction, where the reduction curve is no longer an elliptic curve because there is a singularity. I do like this as if that meant something over Fp, but we sort of imagine there is a singularity, although the curve is just a bunch of points somehow on the plane. So there are now several types of reduction. There is additive reduction if, again, a picture that applies maybe over the reals, not over the same equations. You look at the derivatives, and you can sort of make sense of the derivative the same way. If there is a cusp in the reduction, we say that that's additive. Or there is a multiplicative reduction if I get a node, right? Farther, multiplicative reduction, there is two types, which is these two tangents have slopes, and the slopes can be defined over Fp or over your base field, or not defined over the base field. If they are defined over the base field, that's split. Slopes in Fp, or non-split if the slopes are not in FP. Okay? But it doesn't matter for what Birch and they were doing, it doesn't matter, there's only, because of this condition, all these bad reduction only occur for primes divided with discriminant, so it's only finitely many primes to worry about, so forget about those for now, okay? Forget about the bad primes and reduce. So what they thought is that, okay, maybe for P2, 3, 5, I'm not going to be able to see much, but as P increases, I should be able to start seeing that I have more points over FP than normal if my rank is high. Okay, because the points, if you have a rational point, for most primes I'm going to be able to reduce them. In fact, for all primes I'm going to be able to reduce them if you take them in projective coordinates. You might be worried about primes in the denominator. Just take it in projective coordinates, you can make it all integer coefficients and reduce those. So you reduce those and you start getting points modulo P. So what they thought is that NP should be elevated if the rank is high. Okay? So let's try to put them, let's try to do some sort of average of all the NPs. How did they decide to package those? Was as a product. So let's look at all of them. Look at the product of P bigger equal to 1. Yeah. 2 of good primes. And look at the ratio of NP over P. And see how it grows. Okay? By the way, what they knew there's a theorem, Hasse, that tells you that the number of points on an elliptic curve for a prime of good reduction is between P plus 1 plus 2 the square root of P and P plus 1 minus 2 the square root of P. So it is in the ballpark of P. This P is a subscript. Okay? It's in the ballpark of P, or in fact the ballpark of P plus 1. So you want to know there's this variation, it goes in that interval. So you want to know, so you want to normalize it dividing by P and see how much variation, and if there is rank, you expect that it's going to be leaning towards this side more often than not. Okay? So look at this, and let's cap it with X and see how this grows as X goes to infinity. And what they found that this function grows like constants that depends on the elliptic curve times the logarithm of X to the rank. Okay? So you could actually tell from the data of this graph what the rank was, more or less. Okay? So, so then they started to, they showed this to some people, I believe it was Davenport, that they told him, like, you should put this in some other way, or probably realize that this is,
I think it was Vey.
Vey?
Yeah.
Okay. So they later noticed that, well, you know, NP is actually P plus 1 minus AP, where AP is a trace of Frobenius. It's something called a trace of Frobenius. So this function is approximately the value in quotes at s equals 1 of, so instead of growth, let's see how it goes to 0 if we flip it, 1 over that function. And what they did is look instead at this one. Okay, does that work? So what happens at s equals 1, if you just evaluate, let's see what happens. You get the product of 1 over 1 minus AP times p to the minus 1 plus p, 1 minus 2 minus 1. So what I get is, let's multiply through by p these products. I get p divided by 1 minus AP plus p, so it's p plus 1 minus AP. P divided by that, this is NP, so this is the product of p divided np. So it's the reciprocal of the function they had considered. Okay? So what they now, that log of x is like x, right? So if this grows like x to the RE, then this function should have a 0 of order RE. Okay? So this one should have a 0 of order RE at s equals 1. Now the problem is that this product, we don't know that it converges at s equals 1. We didn't know that it converges at s equals 1. So, so now you can repackage this again and define, you've probably now, you've seen that appear in the construction of the functions of modular forms in Keith's course, and you can define the Hasse, Bay, L function of E as L ES equal product of 1 over LP P to the minus S for primes where, so I'm going to put the bad prime also. So there is 1 minus APT plus PT squared for good primes. 1 for additive primes, 1 minus t for split multiplicative, and 1 plus t for non-split multiplicative. And then the conjecture, the refined conjecture was that you can calculate the rank of the elliptic curve numerically by calculating the order of vanishing of the L function. So the order of vanishing at s equals 1 of L ES is the rank. So in other words, if you write a Taylor series at s equals 1 of the L function of this complex valued function, the Taylor series should start with around s equals 1, it should start with s minus 1 to the r, blah, 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 blah. Okay? Now that Taylor series will have a constant in front of that first term, and they actually go on to the even more refined conjecture. It tells you what that residue, what that value is. And it involves, if you've seen number theory, if you've seen algebraic number theory, the analytic class number formula, there's some theorem of this sort. There is an analytic class number formula that relates the residue at 1 of the Dedekind set of function with essentially all the main invariants of a number field. And here also, I won't write it down, but you also see that the residue at s equals 1, it relates with the size of SHA, the rank of the elliptic curve, the regulator of the points, it relates to the very specific information about the reduction of the bad primes and the size of the torsion subgroup. All those packaged together give you what the residue is going to be over there, plus a period, some integral that tells you some arc length. So I just wanted to show you, since we've talked about this elliptic curve for a while, and I wanted to change to stage for a while, just at least once, because Magma does not have an interface, a graphical interface, but with Sage you can grab these things. So if you take 5077A1, the first elliptic curve by conductor rank 3, you can define its L series, that's the Hasselbeck L series. You can evaluate it at 1, and you see that it has a 0. Remember that elliptic curve has rank 3, so the order of vanishing should be 3. And you can calculate the Taylor series, see what it looks like. Oh, BSD is false. There is a 0 of order 1. Not so much, numerically not so much, because the coefficient is 10 to the minus 22. So it's probably a 0. This is probably a 0. And the first non-zero coefficient is 1.8, and it goes with Z cubed. So it indicates that there should be a triple 0 at s equals 1. Okay? This is the L series, the Taylor series around 1 of up to, I don't know why it goes up to Z this second, but anyway, I thought it was up to Z to the 4. And you can plot. So you see that the graph of the real values of the L function, it does certainly look like there is a triple tangency at s equals 1, as it should from the BSD projection. Okay? So I'll finish here. There's a little more detail on the BSD conjecture in the notes in chapter 5. And something very important I didn't get to talk about is the connection between modular forms and elliptic curve, the theorem of modularity. And that's also, there's a longer exposition there in chapter 5, which I think Keith alluded to in his course too, about what modular forms have infinite products and so on and so forth. So you can read some of that in there. So I'll finish.